Yes.
Okay, good
Yes, it's
morning,
okay.
everyone. I would like you to introduce my topic, which is determining the air resistance of an electric car. And let me start with briefly outline the presentation plan. I will start by discussing why have we undertaken this topic, and next I will introduce you to our research object, followed by a discussion of the research method. The next step of the presentation will be to discuss purpose of the study and the results of the research conducted, and focus on the analysis of the results. I will conclude the presentation with a brief summary. The aerodynamics in vehicles plays a very important role. It not only helps to reduce energy and fuel consumption while driving, but also allows to achieve better results. Aerodynamics also improves cooling of the engine and the vehicle's braking components. Determining aerodynamics resistance of an electric car is important because it leads to minimizing electricity consumption while maximizing the car's performance. The most commonly used methods for determining aerodynamic drag are numerical and analytical methods. Analytical ones involve solving mathematical equations and theoretical flow models, while numerical ones based on concluding computer flow analysis using three-dimensional models of objects. An essential aspect of the numerical analysis and analytical calculations carried out is the verification of their results by conducting tests on a real object in a wind tunnel. In connection with the construction of an electric bolide within the scientific circle, the problem arose of studying the aerodynamic resistance of the vehicle, wanting to design the optimal shape of the shell. The figures shows objects for numerical testing of the aerodynamic resistance of an electric vehicle. These are two selected concepts of previously designed vehicle body and long cylinder reference model. Due to limitations of the calculation, the models have been simplified, but such important details as the driver's helmet, wheels, and roll bar have not been omitted. The concepts reflect in as simplified as manner as possible a real electric vehicle, a visualization of which is shown on the previous slide. The study objects, solid models, were designed using SolidWorks software. The research method consisted of numerical analysis of aerodynamic drag of solid models of prepared concepts and at 1:1 and 1:10 scales. The chosen scale was selected through an analysis from which became clear that at this scale the research would remain accurate, and at the same time, reducing the model by a factor of 10 would allow to build of a wind tunnel for verification of the conducted analysis. Numerical analyses were performed in SolidWorks software using the flow simulation add-on. First, the computer domain of the aerodynamic tunnel was designed, and then a series of analyses were carried out for assumed values of Reynolds number. An important part of the analysis performed was to verify the correctness of the assumed research method. For this purpose, a solid model of a long cylinder was designed whose aerodynamic drag coefficient is known and included in the literature. On the pictures, you can see the wind tunnel computer domain for both 1:1 and 1:10 scales of a long cylinder and its computer model. First of all, the bolide is a pretty large object, so the constructions of both the tunnel and the facilities themselves would consume pretty large resources. In order to verify the correctness of the results obtained numerically, it is possible to build scale models, test them numerically and experimentally, and then compare the results obtained from both types of tests. However, this involves the selection of many parameters, such as appropriate values of Reynolds number and tons wind flow velocity, and cross-sectional area of the wind tunnel test section. The figure shows the design of a wind tunnel for testing scale objects. Performing tests from the aerodynamic drag force of scale vehicles will allow validation of the results of numerical analysis. The figure shows diagram of the performed numerical analysis of the dependence of the value the aerodynamic drag coefficients on the Reynolds number for the first concept of the made bolide model. It should be noted that as the value of the Reynolds number increases, the value of the aerodynamic drag coefficients levels off, as can be seen in the flattening curve on the diagram. The variation of successive points on the x-axis as the Reynolds number increases is less than 2%, which was in agreement with the established parameters. The values of the aerodynamic drag coefficients for the Reynolds number above 150,000 oscillate around 0.4 for both 1:1 and 1:10 scale, which suggests the correctness of the analysis performed for the reduced model. This figure shows a diagram of the performed numerical analysis for the value of the aerodynamic drag coefficients on the Reynolds number for the second of the made bolide model. Analyzing the diagrams of the relationship of the aerodynamic drag coefficients values to the Reynolds number for the second concept, the same trend as for concept 1 can be observed. In this case, the difference between the next points is also about 2%, and also above the value of 150,000 Reynolds number, almost complete flattening of the curve is noticeable. The attached image shows a diagram which is showing the dependence of the value of the aerodynamic drag coefficients to the value of the Reynolds number for the reference 1:1 and 1:10 scale cylinder model. Note the repeated trend of flattening of the curve as the value of the Reynolds number increases. Conducting this analysis helped to confirm the correctness of the numerical analysis carried out. However, the values obtained in this analysis divided from the book values by about 5%. It was hypothesized that this was due to too small cross-sectional area of the designed computer wind tunnel. For this reason, further analyses were carried out for the tunnel model, which was enlarged 3 times, the results of which are attached on the next slide. And in the picture above, you can see the reference model of the cylinder in 2 different wind tunnel models. The first one is the previous one, same as our computer domain for shell tests, and the second one is 3 times larger cross-sectional area. As can be seen from the visible graphs, increasing the computer domain allowed to obtain results in line with the literature, which leads to confirmation of the thesis, which is shown on a third diagram, percent variable reference model concepts. Analyzing the data obtained from the performed analysis, the following conclusions emerge. For both concepts, one-to-ones and scale models, the results obtained were reproducible. The ratio of the value of the drag coefficients for scale 1-to-1 to scale 1-to-10 for concept 1 was about 7% and for concept 2 about 5%. The results of the numerical simulations carried out for the cylinder model were reproducible, and the differences between successive measurement points were less than 1% for both scale 1-to-1 and scale 1-to-10. Conducting analysis for a reference model of a cylinder for the same boundary conditions as for the concepts resulted in a 5% deviation from the literature values for both scaled model and one-to-one model. Running the analysis for the cylinder model in an enlarged computer wind tunnel produced results consistent with the literature, which is 0.82. The percent variables were calculated from the above equation. In a few conclusions, we can say that aerodynamics is a key issue in the design of electric vehicles. Next, the numerical studies make it possible to analyze both full-scale and scaled models, and it is very important to use reference models to confirm the adopted research methods. The numerical studies conducted will allow the construction of an actual wind tunnel for testing scale objects. And the last one, the study of scale objects, allows reliable results to be obtained and lower costs of the project. That's everything from me. Thank you for your attention.